This is the second video for section 3.3. In this video, I'm going to talk about exercises on page 104 and 105 of your workbook. So let's get a blank whiteboard to work with. Okay, so looking at page 104 of your workbook, number one, we're talking about here a table of information that is given to us. So in this table, we're given our input and output, right? Our independent variable is days measured, D measured in days. Our output is N of D, measured as the number of cells after D days. We're told that at 0 days, there's 24,000. At 1 day, there are 30,000 cells. 2 days, we have 37,500 cells. 3 days, we have 46,875 cells. And then at 10 days, it is left blank for us to calculate how many cells that would be. And our last row says that I don't know how many days, but at some number of days, there would be 682,121 cells. So those blanks are left there for us. Our instructions here ask us to determine if this is an exponential function first. And if it is exponential, we identify our initial value, our growth or decay factor, and our relative rate, our relative growth or decay rate. Then we'll write the equation for the function, and we also are asked to use the equation to fill in the missing spots on the table. So let's start up here. Is this exponential? So to determine if it is exponential, we want to look at our output ratios, right? We want to look at the output column and compare each entry to the entry prior to it. That would be the proposed growth rate. So I'm going to compare these values on a separate board just so I have enough space. So my day 1 value of 30,000 compares to day 0's value of 24,000. Right? I make that division and I should see I get 1.25. This should hold true for all of the table's values that I have both pieces of information. So if I look at the next comparison, on day 2, there's 37,500 cells, and day 1 had just 30,000 cells. That again is 1.25 when I divide, and my last comparison is 46,875 cells to 37,500 cells. And again, I get 1.25. So I am seeing something here that is representing having an exponential quality, exponential function. So our constant multiplier is that 1.25. And obviously the number of days is just increasing by 1. I'm ignoring those last 2 rows because I don't have both pieces of information. At the end, after I have an equation written and everything, I'll go in and fill in the information on the table there. But so our equation is something that we can come up with now. So the equation is output equals, so N of D equals the initial value. I don't think I have enough space to write it here. Just get a board. So N of D equals the initial value. So looking at my table at day 0, I know there's 24,000 cells, so that's the initial value, times the growth factor, which I've calculated as 1.25, raised to the d power. So we have our equation. I can identify the pieces of my equation here. So that's my equation I'm working with based on the information in the table. The initial value is 24,000. The growth, it is growth because 1.25 is larger than 1. The growth factor is 1.25. The relative growth rate is how much bigger than 1 is B. So B is 1.25, it's 0.25, which is 25% bigger than 1. So all that's left is to fill in the missing values in the table. So I'm just going to zip back to my table for a second. So we have an input of 10, and we want to know the output. I'm going to deal with that one first. So looking at my equation, n of d, the number of cells, is equal to 24,000 times 1.25 raised to the number of days. So I know the number of days as 10 days. So we can solve this equation. We did things like this in, I believe it was section 2. We can solve the equation. We take 1.25, raise it to the 10 power first, then multiply that times 24,000. And we see that the number of cells after 10 days, n of 10, is equal to, roughly speaking, 223,516 cells. So I'm not using fractions of a cell, just whole cells. So we can fill that in on the table. And look at our last row that we also have unknown information. So 223,516 cells. Now in the last row, we don't know the number of days, but we do know how many cells there are. So looking at my equation again, I know the number of cells now. It's told to me that it is 682,121 cells. So that's the output, equals the initial value of 24,000 cells times 1.25 raised to the d power. I don't know the number of days. To solve this, I'm going to first isolate my growth factor raised to the d power. So first, I want to get the 1.25 times to the d power. I want to get that alone first before I worry about how to exactly solve for the exponent. In a previous example, in a video for, I think, section 3.2, we used like an estimating technique. It was like a guess and check. Here we're going to talk about exactly solving, not using the estimation. So I want to get the 1.25 raised to the d power alone. So I'm going to divide by 24,000 on both sides. So I make that division. I'm going to round to 2 decimal places here. So 682,121 divided by 24,000 on the left here, rounded to 2 decimal places, gives me 28.42. On the right side of my equation, I have a cancellation happening with those 24,000s. So all I'm left with is 1.25 raised to the d power. Now, something that you may or may not remember from Math 099 or previous math courses is logarithms. So I know some of you were in 099 last semester, but I will give just a quick little refresher. about how exponential equations and logarithmic equations can get translated. And we're going to use logarithms here to solve for the exponent. So our exponential equations are some base raised to a power equals a number. Right? That's what we have been seeing a lot of. The logarithmic version, the way to write that as a logarithmic equation, is the same meaning, but just written differently. So it means the exponent is equal, or I should say the power, because I used the word power in mine. Power is equal, I need more space too. Sorry, I haven't had my coffee. Power is equal to the log base, whatever that base is, of that number. So just one example of just a random equation given to you. If you were given an exponential equation, let's say 2 to the x equals 10, that's an exponential equation. I can write it as a logarithmic equation using this idea. So just going to flip back. That's base raised to the power equals number. 2 raised to the x equals 10. So we can rewrite that as x equals log base 2 of 10. Right, so that's the same as saying x equals log base 2 of 10. Now, log base 2 of 10 is something I can compute on a calculator. Depending on your calculator, there's different ways you're going to be able to compute it. So if you have like a TI-84 or higher, there's a different way than what I'm going to show. I'm going to show a way that works for all the calculators as long as you have a button on your calculator that says LOG. So find that LOG button on your calculator. I'll talk about what buttons I'm pressing. I'll make like instructions. But before we go to the calculator to try and solve, I want to notice, right, we were trying to fill in that last part of the table. We started by just plugging in the value we knew, right, our output. Then we divided by 24,000 on both sides. And now we're left with this exponential equation. 28.42 equals 1.25 raised to the d power. To solve this, we're going to rewrite it as a logarithmic equation. So the exponent, d, equals log base, what was the base? 1.25 of 28.42. Now, depending on what type of calculator you have, you may be able to just type in log base 1.25 of this number. Go for it. I don't have a calculator that can do that, and a lot of you probably don't as well. So now let's pull out the calculators, and I'll talk about how to type this in so we can get an answer. So I'm just going to copy the equation we're trying to solve on the calculator, log base 1.25 of the number 28.42. Okay, so in order to be able to use the calculator, I need to make this say just log, not log base 1.25, because the regular LOG button means it means having log base 10, and the regular LOG button, log base 10, is on our calculators. So there's this nice little change of base formula. It's more like a process to understand, but it's not super complicated. So the change of base formula says that whatever my big number is that I'm taking the logarithm of, I'm going to write that as the numerator of a fraction. So log of 28.42. I'm not using log base anything. I'm just log base 10, the common log. and that's the numerator of a fraction. And the denominator, the downstairs, is the log of whatever my base was, the common log of that base. So you should see here, the log base 1.25 became the denominator. And log of 28.42 is the numerator. So instead of talking about it as one kind of log base 1.25, we changed the base to log base 10, the common log, which is a button we have on our calculators. Or if you're really old school, it's something you have a table of, and you could read what the values are reported as. So I'm working with this log base 10 of 28.42 over log base 10 of 1.25 now. Calculate that on the calculator. I want to turn on my calculator, find my log button, hit log, and type in. So this is common log. I don't have to say what base it is. It is base 10 because it's just log. So log of 28.42, close my parentheses. That's going to be the numerator. It's over. So we divided by the log of 1.25, close my parentheses, and hit enter. And if you do that, you should arrive at 14.999, like that. So about 15 days. Now, I'm going to repeat what we're pressing on the calculator to do this, and I'm going to write down the buttons we're hitting. If you have a scientific calculator, graphing calculator, these buttons should still be relatively close to the same. So it's the LOG button, and then it'll open a parentheses for you. You type in your 28 what was the number? 28.42, and then close parentheses button. Okay, you have to close those parentheses. Then we hit our division key. Now we type in the log button again because our denominator starts with a log. And we say 1.25 and close those parentheses. Then hit equals. And that should pop out something like 14.999 ... which we round to 15 days. Okay? If you're having issues with your calculator, like you don't know where the logarithm button is, you're pressing buttons like this and it's not working, we're gonna have to WebEx about it because there's 100,000 different Casios and TI whatevers and different kinds of calculators out there, so I can't guarantee 100% that these exact buttons are the ones you're gonna press, but it's pretty likely. The biggest issue I could see is if you don't have a button that says log on it, you might have to press a couple of buttons to say logarithm. But anything that's a scientific calculator or a graphing calculator will have logarithms, and that's the kind of calculator that's been required for this class. Okay. So that was a very long problem. Guess what? We're going to do one more, and that's it. The other three I'm not going to touch in the video. They're there. You can work on them on your own if you would like. Take a breather, pause the video, relax for a minute, because these are very long problems. We're going to talk about number 5 on page 105 next. So when you're ready, play the video. And it's page 105, number 5. So it's a different table. So I'm just going to copy my table down from my workbook here. So I have all my information on the whiteboard. And if you can hear that car revving, I live in a noisy neighborhood. I apologize, but there's really nothing I can do about it. Okay, so on day 4, again, this has to do with the days and the number of cells. On day 4, we're told there's 20,736 cells. On day 5, 15,552 cells. On day 6, 11,664 cells. And on day 7, 8,748 cells. And then there's 2 other rows in the table that have missing information. We have 9 days and we don't know the number of cells. And then we have the last row where we don't know how many days, but at some point there's only 657 cells. So we're going to work through this in the same way we did the first problem. So first, is this representing something that's exponential? To determine if this is exponential, we looked at comparing our ratio, right? We look at the ratio of the outputs, see if it's a constant ratio, if we always get the same thing when we make the comparison. So if I compare day 5, 15,552, to day 4, which was 20,736, and I do that division, I should get 0.75. And then I do that again, but now for day 6 and day 5. So we have 11,664 compares to 15,552, and we get 0.75. And then one more time for day 7 compared to day 6. So 8,748 compares to 11,664, and again, we get 0.75. So because we're getting the same number for each of these ratios, each of these divisions, that means we do have something that is exponential. So we're able to create an equation for it. We're able to identify all the parts of it, and we'll be able to fill in the missing values on the table. Okay, so let's talk about the equation. So the equation is going to be my output equals the initial value, which I don't know. Day 0 is not given in the table. The initial value, I'm just going to use A for that right now, times my constant multiplier. I was seeing that ratio as 0.75 raised to the D power. So we have something that is going to be decay here. I can use one row of my table and use those coordinates, the output and input, to solve and find the initial value A. So personally, it really doesn't matter which row you use. I'm going to use the row for 7 days. 7 days, 8,748. And I just like to use that row because the numbers are just a little bit smaller. So we're going to plug in 8,748 for the number of cells. I don't want to be writing in red. So 8,748 equals A times 0.75 to the 7th power. And we can compute 0.75 to the 7th power, which is roughly 0.1335. So I'm rounding to 4 decimal places here. And then we divide by that 0.1335 on both sides. Make sure my decimal points are large. It's not looking like a whole number. And we get that the initial value would be 65,536. Okay, so we can actually come up with our full equation now. I'm just going to get some blank whiteboard here. We have the number of cells after so many days equals that 65,536 times 0.75 raised to the D power. So that is our equation. We know the initial value of 65,536. We also know the decay factor of 0.75. The decay rate is something we can calculate. So remember, with decay rates, we want to talk about how much less than 1 is this number, because our number for decay is less than 1. So we say that the decay factor, 0.75, is equal to 1 minus what? Or rather, I'll use the letter R for rate. So that's 1 minus 0.25, right? So we're seeing a decay rate of 25%. Okay. So we've determined that it is exponential. We've written an equation for the function. We identified the initial value, the decay factor, and the relative decay rate. Right? That's A, B, and R. All that's left is to fill in the missing values in the table. So just looking back at my table, the first row with missing information says 9 days, how many cells? So we can use our equation, and our equation to talk about how many cells there are after 9 days. So we say, oh, got turned sideways. There we go. So we say n of 9, the number of cells after 9 days, equals 65,536 times 0.75 raised to the 9th power. And we can calculate, and again, I'm going to round to the nearest whole number because of cells. We're not usually talking about having fractions of a cell. So I perform the exponent first, raise 0.75 to the 9th power first, then multiply by this 65,536. And we should see about 4,921 cells. So that fills in that part of our table. So we get 4,921 cells. The last row with missing information is how many days does it take until there's only 657 cells left. So again, we're going to use our equation. N of D equals 65,536 times 0.75 to the D power. So that's our equation. The number we're using here is 657 cells, but we don't know the days. So I'm going to plug in 657 for my output. And begin to solve. So before I try and rewrite this with a logarithm, I must get my exponential piece alone. This doesn't look like an exponential equation yet. It doesn't say base raised to a power equals a number because I've got that multiplication happening. So because we're still multiplying by this 65,536, it's not exponential yet in the way that I can translate to logarithm. So my first step is going to be to divide both sides by 65,536. It's important to remember this step, otherwise you have an extra number that you don't know what to do with when you try and write it as a logarithm. So we can perform our division, and we should get, I'm going to round to 2 decimal places, 0.01 equals 0.75 raised to the D power. So to solve this, we're going to rewrite this equation as a logarithmic equation first. So just to make sure it's clear, because I don't think I saw this in the textbook or the workbook anywhere, let's just remind ourselves how rewriting it goes. Base raised to the power equals a number, which is what we have right now, right? We have 0.75 raised to the D equals 0.1 or whatever it may be, right? We have 0.75 raised to the D equals 0.01. We're going to rewrite that as the power, so D equals the log base 0.75 of 0.01. I'm going to rewrite it in this way. So let's go back to where we're trying to solve. I'm just going to grab a blank whiteboard. So we have that whatever d is, it's equal to the log base 0.75 of 0.01. I can now rewrite, so that I can use my calculator, I'm going to rewrite the log base 0.75 of 0.01. I'm going to rewrite that as 2 logarithms in a fraction. That's the change of base formula. So that I'm just using the regular old log. My base was 0.75, right? And the base goes downstairs. It goes in the basement. That is like the corniest way to remember, but it can help you if you're having trouble keeping it straight. So that log the log base 0.75 becomes dividing by the common log of 0.75. And then the log of 0.01 just hangs out in the numerator. So I can use my calculator to calculate, and I'm going to round to the nearest whole number for my days. I get that it takes about 16 days for the number of cells to reach 657 cells remaining. So these 2 examples are rather time consuming, especially the last step in solving. So you may want to work on a few other examples or start trying the Section 3 homework early, because you are still expected to be trying these homeworks more than once unless you're getting a perfect score on the first attempt. So you should be attempting the homework multiple times, trying to improve your score. I know it's a lot of work, but you gotta sort of buckle down and do it. And with everything going online and all this, it's made things kind of sticky and complicated, but our demands are still the same. How much we're supposed to get done and what level of understanding you guys are supposed to have is still expected to be the same. Okay, so there will be a third video that has information about the long word problems. So in the workbook, there are 4 of these word problems. I plan to cover all 4 of them because each of them is a little bit different. So other than the word problem situations, you should feel really set and ready to work through some of these equations in solving and things like that. So using just a table or an equation given to you, you should feel more comfortable. But the word problems will be a separate video to talk about. All right, happy studying.